supposedly mathematically proven.
Right. Let me explain to you what a Human transfer is, then we'll do the mathematics of it. Okay? Now, so keep in mind, it's a coplanar transfer, right? Or it's a transfer between coplanar orbits. Okay? And those two orbits have to be circular with the same focus. Let's say this is the first orbit, alright? And this is the second orbit, alright? So the goal is, this is the focus and the center. You with me? This is the initial orbit. And this is the final orbit. Alright? And your satellite is orbiting here. It's at, let's say, this position. This is the perigee position, right? What's going to happen is, when it's at this position, so let's say this is the so we'll call this orbit number 2, and we'll call this orbit number 1. Okay? So this is V1, right? And this is R1. Okay? And what you're going to do is, at this point, guys, pay attention here. You're going to increase this velocity by this much. Let's call this delta V1. Okay? When you increase the velocity at this point, so how do you increase the velocity? You fire your thrusters here, right? In this direction. What's going to happen is, it's going to do this. You understand? This is the transfer orbit. Okay. So what's going to happen is when the thrusters are fired there, it's going to get into this elliptical orbit. Does that make sense? Okay. And when the satellite is here, the velocity of the transfer orbit is, let's say, v transfer. Okay. If it increases the velocity by delta v2, it's going to go into this orbit. Does that make sense? Are you following? How many maneuvers, how many impulse maneuvers did we do?
Two.
Do you see that?
Yeah.
One impulse maneuver is at the perigee of the initial orbit. Okay. The other impulse maneuver is at the apogee of the transfer orbit. You got it? And once you do that, it gets into the final orbit. So see if these relationships make sense. Okay? R1 is RT. You with me? R2 is, or let's call this RPT. Okay, and R2 is RAT. Does this make sense?
What is that? F? Right there?
This?
No, sir. The one under.
This is the, sorry. Okay. That's the thrust.
Okay.
If it fires the thrusters in this, the thrust will actually be in that direction.
Okay.
But it will, it has to fire the thrust in the.
Do we need to illustrate that?
Huh?
Do we need to illustrate that?
You don't have to, so don't worry about it. It's already. You have to just understand that if you want to create thrust in one direction, you have to fire the thrusters in the other direction.
So you didn't necessarily have to draw the other half of the ellipse. Because
You can, yes, you're right. So what can happen is, you may fire your thrusters here, right? It gets into this elliptical orbit. But as soon as you come here, you can fire your thrusters again. But if you want, you can take a couple of laps, okay, a couple of orbits. Just make sure you're okay, and then fire the thrusters when you have to, when you come here. You got it? It's critical that you fire. It's very critical that you fire the thrusters at perigee and apogee, or periaxis and apoapsis. Do you see that? If you fire the thrusters here, it doesn't matter where you fire the thrusters in this orbit, right? Everything is a perigee and apogee. You get it? But when you are in this transfer orbit, you have to fire the thrusters at the apogee. If you fire the thrusters here, it may not get into, it is not a Hohmann transfer. It is not a very efficient transfer. It is not the most efficient transfer.
The focus of the, if we were to fire the thrusters anywhere on the transfer orbit, would the focus be different for that
Focus will not be different. Focus will be the same. So what's going to happen is if you fire the thrusters, see, you have to buy. What is the largest orbit you can get into in this orbit? Apoapsis, right? You see that? If you fire thrusters here, this will be your apoapsis. Your orbit will become, depending on how you fire it, your orbit will become. It's not the biggest orbit. The biggest orbit you are going to get is here. Does that make sense? And that is the reason. Does that start to answer your most efficient, fuel efficient question?
So you're saying you save more fuel if you.
You're going from. This is the initial orbit. Okay, you're going from initial orbit to the largest possible orbit for that fuel. You understand? So you do these two maneuvers, and if you do it according to what Oman suggested, you're going to get into that largest orbit for that same amount of fuel. If you expend the same amount of fuel and fire it here, you're going to get into a smaller orbit for that same amount of fuel. You understand? It's like you're already going here, right? The farthest. Why not fire it there and get the most benefit? Okay, we'll
I have a question. So the elliptical orbit apparatus is touching that second final orbit.
Yes, so this is it's true for any orbit transfer. When you transfer orbits, there is always going to be one point common, at least one point common. Between these two orbits, which is that point common? The perigee. This is the perigee for both of them, right? Between these two orbits, this is the apogee for the transfer orbit, but this could be the perigee for the final orbit. Does that make sense? Because this is still the closest point. Once you select your perigee for circular orbits, once you select your perigee, you stick with that, right? It's not defined per se for circular orbits because the distance is pretty much the same.
First, why is having a bigger orbit more efficient?
For the same amount of fuel, you're going a greater distance, right?
Right.
So what is fuel efficiency? Fuel efficiency is how much it can take you farther, right? So if your goal is to get into this orbit, the best way to do it is Oman. Or the most fuel efficient way to do it is Oman.
And where is R2?
Yes, I'll discuss that. So R2 is this, right? You can say this is R1, right? This is R2. Does that make sense? This is the same as this is RP or RTP, and this is RTA. Yeah. 80, you're right. I'll just follow it. Because this distance is the same as this distance, right? This distance and this distance are the same. Does that make sense? So you have R80, which is the apoapsis of the transfer, that is R2, alright? And R1 is periapsis of the transfer orbit. Okay. What is V? So I think we'll use this. use this notation. Can I just use RP and RA? Okay, we'll just use that. Okay? So you know that corresponds to the transfer orbit. What is V1 or VP is what? V1 plus anybody? No? Got it? VP is this, right? Okay. And V2 is V. Okay. So this is what? V2, right? Okay. And see if you can follow this map. Eccentricity is what? RA minus RP divided by RA plus RP. What eccentricity I am referring to here? What is the eccentricity of this first orbit? Zero. Circle is 0. So here you can see that, right? If it is RA and RP are the same. What is the eccentricity of second orbit? Of the final orbit? 0 again. What is it?
It's still going to be a circle.
It's again a circle.
Okay.
Are you talking about the transfer orbit?
The transfer orbit is that. Does that make sense? Now, RP
Bless you.
is h square over mu divided by 1 plus e cosine theta, or 1 plus e, right?
What's that subscript? Is this how the vertices?
Hmm?
Or what's that subscript?
This one?
Yeah.
RA. Okay. RA and RP are referred to the transfer orbit. Okay. So if I substitute E here, I'm going to get h square over mu RA plus RP divided by 2A. Two RA. We can do the math if you want. All these computations are for transfer orbit. Okay. H is what? root of 2 mu into root of RARP divided by RA plus RP. Okay. Here's your test, and this will tell me if you're following this material. Where is the angular momentum vector of these three orbits? What direction is the angular momentum vector?
The angular
Momentum vector.
So it should be opposite of the force we draw.
Huh?
It should be opposite direction of the force we draw.
Towards the focus. How? I mentioned this earlier. How are we supposed to do it when you only have one? Like you just have one center of point compared to typically where we had a.
This is the simplest, very simple question.
Small VP.
Hmm?
The same direction of VP.
Is it in the
direction of the focus?
Direction of the focus from where?
Yeah.
Or from the satellite.
satellite's position?
Angular position vector, momentum vector is this. Okay?
Everything's rotating around.
Everything is rotating around it. Axis of rotation is what? This, right? So angular momentum rotation, angular momentum vector is, it's the axis of orbit. Okay, it's coming out. There are, what is angular momentum vector what element or what part of the orbit does it define? What does it define? There are three categories, right, in the orbital elements.
It's the size.
The size of the orbit, right? So if you see, H1 would be smaller than HT, and that would be smaller than H2. Does that make sense? H1 will define what? The size of the initial orbit. You get it? H2 will define what? H2 will define what? Size of the final orbit. And HT will define?
Size of transport orbit.
You get that? So H1, which will come out the most? H2. You got it? This H is what?
Specifically it's
This is
That is,
HT.
okay. Huh?
It's HT, right?
HT. This is the H of the transfer orbit. Okay. You don't want to be so foundational that you define the whole thing again. So this is the HT, transfer orbit. Does that make sense? And you should realize that this is not the same as, what is same? The only thing which is similar is R. V is different, H is different. Alright? So if you have V is equal to root of 2 mu root of 1 over R. goal? Think as a spacecraft engineer. Okay. What would be a goal in this?
Save fuel.
You want to figure out the velocity so you know how much propellant to use and what burn rate.
Very good. What your goal is, to figure out what is your goal. Your goal is to get to this, right? To get to this, as an engineer, what you are going to do is you will need to compute the amount of fuel which is needed. You understand? And the amount of fuel needed is a function of what? Yesterday, what did we see? What did we say? Delta M is a function of
1 minus 2.
is a function of what? Hmm? Try to understand when I say it's a function of. What is it a function of? I'm not asking you the expression. Delta M is what? Is a function of what?
Rate of fuel consumption.
Hmm?
Rate of fuel consumption.
Delta M is rate of fuel consumption. What is it a function of? Huh? Delta V. Delta M is rate of fuel consumption here. Okay? You got it? Here, why do we say, when you say function of, right? Why do you say it's a function of? Why is it not a function of this? Huh? It's a constant. Why is it not a function of this? It's a constant. Why is it not a function of this? This? All those are constant. If you see delta M is a function of delta V. Once you know delta V, this is this known? Yeah. That is the spacecraft mass. Is this known? ISP? You choose the fuel, right? You see, this is how you have to, even when you do the final design, this is how you size your aircraft, size your rocket. You understand? So you see delta M is a function of delta V. And you have to connect. Now are you trying to connect your orbital mechanics knowledge? Right? So you see delta V is, ultimately you're trying to do what? This is your goal, okay? Final goal. To figure out delta M given ISP. Right? Delta M is function of delta V. Delta V is delta 1 plus delta V1 plus delta V2. What is delta V1? Vp minus V1. Right? What is V2? Delta V2 is V2 minus Vt. Right? You know you have to get into this orbit first. Right? As a spacecraft engineer, where does your design start here? As a spacecraft engineer, not as a rocket engineer or a rocket scientist. So you will be divided, right? If you go into the industry, you'll be working on rockets, aircraft, spacecraft. You may not work on spacecraft and rocket. You understand? This is a really nice bifurcation. What is the role of a rocket engineer or a rocket scientist? To design rockets, but to get you into a specific orbit. Okay? And we are talking about rockets. When we talk about rockets, we are talking about launch vehicles. Okay? So the launch vehicle will get you where? Specifically here, where will the launch vehicle get you?
initial orbit. You get it? Your role as a spacecraft engineer will start once you get here.
Once you're already in.
Yeah. So the launch vehicle will get you from here to, this is Earth, right? Somewhere here is the surface of Earth. So that rocket will launch it, the launch vehicle will go out and it will deploy you somewhere on this orbit. That's when you start designing your transfer. You see, you know your M, you know the spacecraft mass at this point, right? You need to figure out, you know what this will be defined, right? You're saying, you said, we need to get into a 2000 kilometer circular orbit to do this observation. So if you say 2000 kilometers, what is that value? 2000 kilometers. If this orbit is 2000 kilometers, what is that value? Huh? It is R2 minus
The other one.
R2 minus radius of the Earth. You got it? No, RP is not radius of the Earth. Radius of the Earth. The 2000 is altitude. You cannot get into a 2000 R. What will you do if you get into 2000 R? If R is 2000, where are you? In the Earth. 2000 cannot be RP, RA, anything like that. You're inside the Earth if R is. So you have to add that 6378. So you have to, that R 2000 is R2 minus RE2. Okay? So you add that.
Would it be plus?
Yeah, I thought it'd be plus 2.
2000 is what? I'm saying 2000 is R2 minus RE. R2 is what? 2000 plus RE. That make sense? I was asking this.
Oh, okay. I got it.
Okay. R1 would be something like 500 or 500 minus RE. So you are given all of these and you are trying to figure out. You do the design. Okay. We'll start looking at what does this mean. This V is
That VP1.
Forget about this. Okay.
this V is if I say V1, this will be R1. Okay. If I say V2, this will be R2. Alright. We'll talk about the next one. Any questions? You good?